week 4. All right. And for quiz 2, the contents are from week 5 to week 8. And then for end term, you will have all the entire syllabus. Okay. So here I will quickly tell you about week 1 to week 4. What are the things we are going to see in week 1 to 4? So in week 1 to 4, you see that the first 2 weeks mainly we see mostly matrices. Okay. So here the first topic is, so this one, if you see, so this topic mainly we are talking about matrices. Okay. So here system of linear equations, we are just giving the relationship between matrices and system of linear equations. But the main part of system of linear equation comes in week 2, where we see how to solve system of linear equations. So we have like 3 different methods we see in week 2. And then in week 3 and week 4, we are doing vector spaces. Okay. So all these things may look like different topics. So week 1, you are looking at matrices. Week 2, you are solving system of linear equation. Week 3 and week 4, you are doing vector spaces. So you may think that they are different topics, but you will see that as you proceed, you will see that all of these are interlinked. Okay, they are not different at all. So everything is linked. And one important thing everyone should remember is that out of all the entire syllabus, week 1 to 4, I can say that it is comparatively easier. So please don't miss to score to your maximum, put your maximum effort for week 1 to week 4, so that you can improve your marks maybe. Okay, so in the point of scoring marks, week 1 to 4, they are comparatively easy. So please put more effort and try to score as much as possible in quiz 1. All right. Okay, fine. So today we are going to start with week 1. So mainly we are going to introduce vectors and matrices. So we will introduce vectors and the operations are vectors, and then we will introduce matrices and see what are the different types of matrices and the operations of matrices. System of linear equation, I will try to start if time proceeds. Okay, if time permits, then I will also start with system of linear equations. All right. So what is the word vector reminds you? So vector means usually you think about so something which has both magnitude and direction. This is what you usually see, right?
Yes, ma'am.
Yeah.
Yes, ma'am.
So, but in our case, so what is a vector? What is vector in physical context? A vector has something which has magnitude and direction. It means what? So you say that you start at this point and then this is the direction. This arrow mark is pointing here. So this is the direction, and the length from D to E is the magnitude. Okay. So the length of the line shows its magnitude and the arrowhead points in the direction. So this is what you say, both magnitude and direction. Okay. But in our course, what is a vector? Let us see. So before that, we are going to see a few examples to have an idea of what can a vector look like. Okay. And from where do we get these vectors? Okay. So vectors, literally, you can see vectors everywhere. For example, you see a very small data here. So vector can be thought of as a list. So here, the dimensions and weight of a set of 8 carton boxes are given here. So these carton boxes, so the length, height, width, and weight, all these measurements of these 8 boxes are listed down. Okay. So now either you can consider the vectors as maybe all the dimensions of each carton. So for example, what are the dimensions of carton 4? Can you say?
4.5, 1.8, 1.7, 1.3.
1.8, 1.7, and 1.3. So this is the uh, vector which denotes the measurements or dimensions of your carton 4. Otherwise, so this is just saying one particular carton, but all the different dimensions. Instead, what you can say is that you want to look at only the length of all the cartons. So in that case, how does your vector look like?
4.7, 4.5.
4.7.5, like column wise vector.
Yeah.
Up till 4.5.
4.3, 4.5, 4.5. Right? So you see that these are the rows. These are the rows. And what are these? Each of this? They are the
Columns.
columns. So how many rows do you see?
8.
8 rows. Totally you see 8 rows are there. And how many columns are there?
4.
4 columns are there.
4 columns.
4.
Okay. So now you see that you can either consider only one particular carton and all the dimensions of it, or one particular dimension and the all the measurements of all the cartons. So you can look at the list, okay, and you can either look at the row or the column. So both of this represent a vector. Okay. So another example is here. The number of passengers traveling in different time interval for 16 trains traveling from a specific starting point is given below. So here you have another set of data where you have different trains and you have the number of passengers in each time interval. So first 15 minutes, 16 to 30 minutes. So like this, they are giving the number of passengers in each time interval. Okay. So here also the same thing applies. So how many rows are here? Can you tell me?
16.
16 rows. And how many columns are here?
5.
5.
5 columns.
5.
Right? So can you tell me what are the different number of passengers for train number maybe 9?
46.
46, 71, 72, 82, and 6.
Okay. So can you tell me the number of passengers in all the trains between the time interval 46 to 60?
16.
16,
0. 0. 0.
0,
27.
0,
0,
77, 82,
82,
99,
28,
28, 19, 0, 20, 0, and 59.
59.
Okay. So now this represents the column vector given here. Okay. So you see that vectors can be either columns or rows. Okay. So now how to perform, what is a geometrical view of this? We will see maybe after a few slides. So first let us see how to perform arithmetic operations on such list such as tables of columns or rows. Okay. So here is an exercise. The marks obtained by Kartika, Romi and Farzana in quiz 1, quiz 2 and NSEM with the maximum marks for each exam being 100 or shown in the table. So this is the table given to you. Okay. So now look at these options given to you. Choose the following set of correct options. So marks obtained by Romi in quiz 1, quiz 2 and NSEM represent a row vector. Is that true?
Yes. Yes.
Yes.
Yes, ma'am.
So can you tell me what is that row vector?
33, 41, 45.
45.
Yeah. So you see that this is a row vector. So this is the correct option. Okay. Fine. And what about the option 2? Quiz 2 marks of Kartika, Romi and Farzana represent a column vector. Is that true?
Yes, ma'am.
Yes.
Okay. What is that column vector?
Yes, ma'am.
50, 41, 21.
Yeah. So this is also a correct option. Number of components in column vector representing quiz 2 marks are 9.
False.
False.
So how many number of components in column vector representing quiz 2 are there?
3.
You only have 3 components, right? So this is an incorrect option.
Yes, ma'am.
Number of components in row vector representing Romi's marks. How many are there?
3.
So you see 1, 2, 3. Right? Number of component in Romi's marks, you see 1, 2, 3. So you have 3 components. Okay. So each of this represents a component. Okay. So here you see that this is a row vector with how many components?
4.
4 components.
4 components.
And this is a column vector. And how many components are there?
7.
8.
8.
8 components, right? You have 8 rows. So 8 components are there.
Ma'am, is that the notation of a vector?
Sorry?
That bracket. The bracket, is that the notation of it?
Yeah, this bracket is just a notation.
Okay.
And what about this row vector? How many components are there in this row
5.
vector?
5.
This is 5.
5.
And what about the next column vector?
16.
15.
16.
So this is a column vector with 16 components. All right. Okay. So you understand now what is a row vector and column vector and what are the components. So let us see more exercise. In order to improve her marks, Farzana undertook project work and succeeded in increasing her marks. Her marks became doubled for each exam. So Farzana is putting some effort and trying to increase her marks. So her marks is getting doubled, okay, for each exam. So if the mark is doubled, what happens to the, so this is the old marks. So what are the new marks of Farzana? Can you tell? In quiz 1, in quiz 2, and in
76,
N7.
42 and 70.
Yeah, so first one is
76.
76,
42
42,
70.
and
70.
70.
So these are her new marks, right? So these are her new marks of Farzana. So now what is option 1? To obtain the marks obtained by Farzana after completion of the project, scalar multiplication has to be done to the row vector representing Farzana's marks. By the way, we have not yet started looking at what is a scalar multiplication. But anyway, I will just quickly tell you, scalar multiplication means just multiplying one number to all the all the components of the vector. So are we just multiplying one number to all the components of the vector? This
Yes,
number
ma'am.
2.
Yes, ma'am.
Yeah. So we multiplied 2 with this row vector. So what we did 2 times of 38, 2 times of 21, and 2 times of 35 to get this vector 76, 42, 70. Correct? Okay.
Yes, ma'am.
So this option 1 is correct. So what is option 2? To obtain the marks obtained by Farzana after completion of the project, scalar multiplication has to be done by 1. It is correct or incorrect?
False.
Yeah,
This is
it
a
is
false.
incorrect.
Ma'am.
Correct.
Okay. After the completion of the project, the row vector representing Farzana's marks is 76, 42, and 70. Is that correct?
True. Correct.
Yeah. Okay. After completion of the project, again, so here some different number is given. So obviously it is incorrect.
False.
Yeah.
Incorrect.
After completion of the project, again some other mark is given. So again it is
Incorrect.
False.
Yeah.
False.
Okay. So the next exercise is here. So up to this, is everything clear?
Yes, ma'am.
Yes.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay, fine. Okay, so the next problem here is following Farzana's improved marks due to her project, her marks became doubled for each exam. All students were given bonus marks in quiz 2, which is given by the column vector 10, 12, 15. So these are the bonus marks for each student in quiz 2. What will be the column vector representing final marks obtained in quiz 2 by Kartika, Romi, and Farzana? Okay, so first we are improving the marks of Farzana. So what are the new marks of Farzana?
76,
42
42,
and 70.
70.
And
So you
70.
forget about this old mark. Okay, because after this only the bonus mark is given. Okay, and what are the bonus marks for quiz 2? 10, 12,
10,
and
12,
15.
15.
Yeah. So here for already quiz 2, what is the existing mark? What are the existing marks?
50,
50,
41,
41,
42.
and 42.
42.
Now what is the bonus mark?
This is 60.
10,
10,
12,
12, and 15.
53.
Okay.
15.
So now what is the updated quiz mark? Quiz 2 mark?
60.
60, 53,
67.
57.
60, 53, and
53, and 57.
67.
57.
Okay. So these are the things
57.
we first observe. Okay. Now with this given,
Ma'am,
57, ma'am.
60 is not 67, it's 57.
oh yeah. Yeah. Okay. I guess here the question part is missing, but I guess with this given data, you will be able to answer this, whatever questions were given, you will be able to answer. Okay.
Yes,
Fine.
ma'am.
So up to this, is everything clear? Yeah.
Yes, ma'am.
Ma'am.
Okay. Fine. Okay, so what will be the column vector representing the final marks? So the question is here, we just have to give the answer. What is the answer? What is the column vector representing final marks in quiz 2 by Kartika, Romi and Farzana?
60,
60, 63, and 57.
And 57.
Okay, fine. Okay, so moving to Euclidean spaces now. So first we will start with real numbers or real line, which you already know very well. So you have completed one full course on max. So max 1 you have done. So you know already what are real numbers. So any number except complex number, you call them real numbers. So all the integers, all the rational numbers, all the irrational numbers, everything together, you call them as real number. Okay. So what are not real numbers? So what are imaginary numbers? You represent it with I, right? Which is square root of -1. So except imaginary numbers, so numbers of the form a plus ib, in fact, and also infinity. So these are not real numbers. Okay. So the number line, you see, if you draw a horizontal line, okay, and you put a point where you consider that as a 0 point, then that line you can call it as a real number line. And here you can plot all the numbers, all the real numbers. Okay. You can plot integers, rational numbers, irrational numbers, everything has a place on the real number line. So the real numbers are a set of numbers, and the real number line just is a representation of all this real numbers. So it is the graphical way to see what are real numbers. Okay, fine. So what is the Euclidean space Rn? So real line, real numbers, we know. Now what is Euclidean space? Okay, before even going to Euclidean space, okay, so now you have only one line. Now if you have two lines like this, so you have one x-axis here and you have y-axis here. So now you are in a 2D space. So if you take your paper, or if you just consider one wall, so that represents a 2-dimensional space, right? And then if you go to 3 dimensions, suppose you are considering the room you are in, you are considering a box. Okay, all these are like 3-dimensional figures. So they have like x, y, and z axis. Okay, so here you see that Euclidean space is a generalization of all the spaces R, R2, R3. So it is a generalizing Rn, because only up to R3 we are visualizing. That's why only up to this I have shown. And general Rn we cannot visualize like this. So we have a way to represent them. Okay, so what is this Euclidean space Rn? The set of all n tuples. So n tuples means, so you have like n components like this. So this n components together, where this each of this xi's vary from R, this is called a the set Rn. Okay, so this is nothing but your set Rn. So Rn is equal to this set. Okay, so for example, what is R2 then? R2 is nothing but the set of all x comma y, where your x and y vary from R. Okay, so what are this xy? Xy, just like real numbers or points on the real line. So this x comma y are points in R2. Okay, now what is this x and y representing? X represents the distance of the point from the origin along x-axis, and y similarly along y-axis. So this may look quite abstract. Let us look at a graph, so that then it will be very easy. Okay, so for example, if I am considering this point, can you tell me what are the coordinates of this point?
1 and 3.
1 and 3.
1 and
1
2,
and
right? So now this 1 represents the distance of this point from the origin along x-axis, right? And this 3 represents the distance of the point from origin along the y-axis. So that is what is mentioned here. Okay. Similarly, suppose I am considering maybe minus 3 comma minus 2. Okay. So now you see that. So you are like in the negative direction. So you are 3 units from 0 along x-axis and 2 units from 0 along y-axis. Okay. So this is the point minus 3 comma 2. So you can either represent it as a point, or sometimes we also represent them using this vector notation. So you can represent it like this as well. But always in our course, we start a vector from the origin. Okay. Fine.
Yes, sir.
So
Yes,
a point A comma B means it is a vector A comma B. Okay. So you can also represent it as AI plus BJ. Okay. So here I means 1 unit of unit vector along x-axis. J means the 1 unit the unit vector along the y-axis. Okay. So this is this point. I is this vector. This is your I vector. This is your J vector. Okay. Fine. So how do you visualize? You consider it as an arrow from the origin to A comma B. Okay. So now you have seen vectors in R2. So you know how to add, multiply or subtract numbers, real numbers. Now how do you do the same for R2? How do you add or subtract 2 points from R2? So maybe let us take 2 different points. Maybe I'll use some other color. So maybe I'm taking this point here. What is this point?
2,
2,
3.
2.
Okay. And what is this point here?
3, 0.
3,0.
Okay. So we have considered 2 points. So this is 2 comma 2 and this is 3 comma 0. So you have this vector and this vector here. All right. Now,
Yes.
how do you add 2 vectors? So you can do simple component wise vectors, but geometrically, this is how you can view it. So you have 2 vectors V and W. So let us say that this is your V and this is your W. Okay. So now where is your V plus W? V plus W is the diagonal of this parallelogram. Okay. So now let us write what is 2 comma 2 plus 3 comma 0. So what is this? If you do component wise addition, component wise means first
5
component of this vector with first
5 comma
component of
2.
this vector.
5, 2.
Yeah.
Comma 2.
So this is
5,
5
2.
comma 2. Right? So where is 5 comma 2? So here it is not covered. So it should be somewhere here. Okay. So where should be 5 comma 2? It is here. Correct?
Yes, ma'am.
Yeah. So you see that if you consider it now as a vector.
This is V plus W.
Yeah. Okay. So now this is the diagonal of this parallelogram you have considered. Okay. So this is your V plus W. Okay. 5 comma 2 gives your V plus W. So component wise addition, how do you visualize? You can visualize this as these 2 vectors forming the sides of the parallelogram, and V plus W represents the diagonal of this parallelogram. Okay. So this is your V, this is W, and this is V plus W. All right. Okay. So now in general, if you take 2 vectors from R2, how do you add them?
X component
X,
and Y component.
x1 plus x2 and y1 plus y2.
So if you are having negative coordinates, does that make any difference?
No.
No, ma'am.
So for example, let me take maybe minus 3 comma 0, and then you take maybe minus 2 comma minus 3.
This is a
So in this case, what happens?
5 comma
Minus
minus
5
3.
So
minus
again,
5
it is
minus
simply
3.
minus 3 minus 2 comma 0 minus 3,
Minus
which
5
is minus 5 comma
minus 8.
minus 3. Okay. So if you want to do the visualization also you can do. So this is the point minus 3 comma 0, and this is the point minus 2 comma minus 3. So you will have a perfect rectangle, and that diagonal will represent you the
sum of
sum of these two vectors. So you have minus 3 comma 0, and you have okay, so here minus 2 comma minus 3 is here, not a rectangle. So I'm not considering minus 3 comma minus 2, it is minus 2 comma minus 3. So you are having this point and this point, and then so maybe I'll use this color. So you have a vector here, you have another vector here. Okay, so now you see that the sum of these two vectors, you have to complete this parallelogram and then draw minus 5 comma minus 3. So you have to just extend this line and you will end up here minus 5 comma 3. Okay, the visualization and everything remains the same even if you have negative coordinates. So this is what is the parallelogram law, and you call this as component wise addition. This is component wise addition. All right. Okay. So now in this course, by a scalar, we always mean a real number, but you can remember that in general, that is not the case. So scalar usually represents to any element of a field. So what is a field? What that is a completely different topic. For now, we will stick to scalar means real number. Okay. So in general context, field means you can have real numbers, complex numbers, you can have rational numbers. So many possibilities are there. So for our course, we always mean a real number by a scalar. Okay, fine. So now what is mean by scalar multiplication? Okay, scalars usually we use Greek letters. Okay, like x, y, a, b, all these things we are using for representing components of vectors or vectors itself. Whereas for scalar, we usually use Greek letters, or sometimes we use maybe K or C, something like that. So usually alpha, beta, gamma, this kind of notations we use for scalars. Sometimes, yeah, K, C, all these are also used for representing scalars. Okay, just to
Ma'am,
represent real numbers. Yeah, is anyone asking any question?
are alpha, beta, and gamma Greek? Are they related to Greek?
Okay, so you are asking, are they Greek letters?
Yes.
They are.
Oh, I don't know.
Greek or Latin or whatever, that does not matter to us. So I'm just saying alpha, beta, gamma represents the scalars here. Okay, fine. So here, what I'm saying is that scalar multiplication means we have already done the scalar multiplication. If you remember, in this problem, see, you are having a vector, you are multiplying by a real number. This is what is called as scalar multiplication. Okay, so any vector, if you are multiplying each of the component by a scalar, that is scalar multiplication. For example, maybe let us consider this vector 1 comma 1. Okay, so this is 1 comma 1. So what happens when you multiply, for example, 2 with 1 comma 1? What is the vector you get?
2 comma 2.
2 comma 2. Okay. Now, what will you get when you multiply 4?
4 comma 4.
What about multiplying with a negative number?
Minus 3
Minus 3.
Minus 3.
Okay. So what do you observe? What do you observe?
We're
Let
getting
me
same.
draw a line and then you see what you
same.
observe.
They're passing through origin.
They all lie on the same line.
All points
Yeah.
lie on same line.
Exactly.
All points lie on a single line.
Exactly. So what happens? So the geometrical representation of vector addition, it is given by parallelogram law. So for scalar multiplication, it is much simpler. What is that you need to remember? So the new vector lies on the same line. Okay. So whatever is your alpha, suppose you consider alpha is a real number. Okay. And then you consider any vector v. V is any vector from R2. Okay. So alpha v always lies along v. Whatever is the line in which v lies, the same line, alpha v, whatever is your alpha. So it can be positive, negative, whatever it is, it will still remain on the same line. So for example, this is your line y is equal to x. So like this, so every vector you can find an equation, and that scalar multiple will always lie in that same line. Okay. And one more thing. So what happens if alpha is positive and what happens if alpha is negative? What do you observe? So when you are multiplying with a
It
positive
is
number,
above
what
and
happens?
it above the original
Look,
point.
let us look at another point as well, maybe with a negative coordinate as well. So maybe minus 2 comma 1. Let us consider this point. Now if I'm multiplying with a positive number, let us say by 2, then what is the number I'm obtaining?
Minus 4, 2.
Minus 4 comma 2. And suppose I'm multiplying with a negative number, maybe minus 2, then what happens?
4, minus 2.
Yeah. So it is 4 comma minus 2. So you see that. So if I'm considering this as my vector v, so this is 2 times of v and this is minus 2 times of v, right? So now all of this lies on the same line.
Same line.
Okay. They lie on the same line. What happens when you multiply with a positive number?
Same
It is
coordinate.
above the point. The same.
So it is extended in the positive direction, right? And if you multiply with a negative number, it is extended in the opposite direction. So you can say that the vector gets extended. So here the vector gets extended or even shrink. Maybe if you are multiplying by 1 by 2, so you can say that the vector lies along the same direction of v. The vector lies in the same direction of v. For example, if I am multiplying by minus 1 by 2, then 1 by 2 if I am multiplying, then you will get minus 1 comma 1 by 2, this point. So it is always not elongated, it can also shrink also. So I am writing the vector lies in the same direction of v. But what happens when we multiply with a negative number? The vector lies in the
Opposite
Coordinator.
opposite direction of v. Okay. So here opposite direction of v. So maybe for example, just for clarification, if I'm taking minus 3 comma minus 2. So now if I'm multiplying with a positive number, then what happens? For example, if I'm multiplying with maybe 2, then what happens?
minus
Take
6
minus 6 comma minus 4.
Extend, ma'am. It will extend.
same direction.
So it will be in the same direction. But if you are multiplying with minus 1, then what happens?
It will extend in
will
opposite
The
direction.
opposite direction. That point will come here. Minus 3 comma 2. Minus 2 will become 3 comma 2. So it is now in the opposite direction. Okay. Fine.
Yeah.
So this is what
ma'am.
Yes,
you should
ma'am.
know about scalar multiplication. Yeah.
Ma'am, is it true that all these vectors will pass through origin?
Sorry.
I mean, is it true that all these vectors
I think in
will
our
pass
course we
through
will
origin?
consider from zero.
Huh?
All these vectors.
Will
Ma'am,
pass through origin.
he's asking that all these lines are necessary to pass through the origin, or
Yes,
the lines
usually
can
in
pass
this
through it.
course by a vector, we always consider a vector from origin. Because as I told you, the definition itself says that what is A comma B? A represents, X comma B, X comma Y. X represents the distance of the point from origin, not from any other point. From origin along x-axis, and Y represents the distance from origin along y-axis. So always from the origin. Okay.
But vectors we can move anywhere now. They have same value.
Yes. So in that case, okay, when we move to maybe vector spaces, there you can ask me the same question. So there we generalize Euclidean spaces and call them as vector spaces. In that space, we do not call it as origin. Instead, we call it as a additive identity. Okay. So, so that case, additive identity can be any number, and you can shift the origin to some other number as well. Okay. So that concept we generalize as vector spaces, but for Euclidean spaces and for this particular way of defining vector addition and scalar multiplication, vectors are always from origin. Okay. Fine.
Yes, ma'am.
Okay. So now
One more question.
vectors in R3. So how do you look at a vector in R3? So I have given a GeoGebra link for you. Those who want to check at this link, you can check. So just I have plotted, it's not something big. I have just plotted 2 points.
I'm going to share that in chat.
Yeah.
I'm unable to access that link.
So let us see, you are having X, Y, and Z. Okay. So let us say this is 1, 2, and you have 1, 2, 3 here. Okay. And let us say this is 1, 2, and 3. So for example, maybe the negative direction also I can plot if you want. So this is -1. Okay. So where is the point? 1 comma -1 comma 2. Okay. So you see that now XZ is now forming a plane. Okay. So there 1 and 2. So somewhere here. And then -1. So it is below this point. So approximately you can say here 1, -1, and 2. Okay. So you will have a better visualization in this GeoGebra. Let me see if I can open this. Maybe in, sorry, different page. Just give me a minute.
Ma'am, in the chat box, someone is like even this GeoGebra link. You can go there.
Sorry, what is that you are saying in the chat box?
Someone has pasted this GeoGebra link.
Okay, fine. Anyway, I am projecting it here now. You can.
No, that link is not representing this.
Okay, fine. I will show the image.
Ma'am, can
here,
you share
don't worry.
this link in chat?
Yeah, I will
We
do
can
that.
see.
But you can view it now. So are you able to look at this GeoGebra page?
No,
Yeah.
No, ma'am.
No, ma'am.
No? Okay. Okay, so no issues. I will just maybe show it in.
Shared the wrong screen.
Yes,
Give me
ma'am.
a minute. I will share. Maybe we will not waste time here. We will just continue, and at the end of the session, I will open another page and show. So this is just for visualizing a vector in R3. Okay, nothing much.
Okay, okay.
So the same kind of vector addition and scalar multiplication concept works here in R3 as well. So if you take any 2 points here, how do you add? So
Your
for
screen
example,
is
1
not.
minus 3, 2. And
Ma'am,
then
I
you
got
have
it.
5.
Ma'am, are you writing something?
The presentation is not there.
Okay. Fine. So you see that if you have two vectors, how do you add them? What is the sum of these two vectors?
This is 6.
Ma'am,
3 and
6
2.
minus 6, 3,
6, 3, 2.
and 2.
Okay, so here also the same component wise addition. Okay, so here what about the scalar multiplication? For example, maybe minus 2 times of 1 comma minus 3 comma 2. What is this vector?
Minus 2 comma
Minus 2,
and 6
6,
comma
and
minus 4.
Minus 4.
Minus 4.
Okay, so this is your vector. So how do you do addition and scalar multiplication is exactly the same. So for this course, remember that vectors means rows or columns of numbers always. Okay, so either you represent it like this or you represent it as a column. Okay, so in general, how do you write vector addition and scalar multiplication in Rn? So in Rn, any vector you represent it as x1, x2, xn, and another vector maybe y1, y2, yn. So what is the sum of these two?
x1 plus
X1 plus
X1
X
plus Y1,
plus Y1
comma
till
X2
Xn
plus
plus
Y2,
Comma
Yn.
x2 plus y2, comma
Xn plus Yn.
Okay, and alpha times of alpha is any real number. So alpha times of x1, x2, xn is
Alpha X1,
x1
comma
alpha times
alpha X2,
x1, comma
comma
alpha times
alpha
x2
Xn.
plus.
Okay, so this is how you define vector addition and scalar multiplication in Rn. Okay, fine. So let A and B are two vectors. Suppose CA plus 3B is equal to 4JK, where C, JK are real numbers or scalars. Find the value of C. So how do you do that? So what is CA plus 3B first of all? This is your LHS. So what is CA plus 3B? C times of 1 comma 1 comma 1 plus 3 times of 2 comma
2 comma
minus 1
minus 1
comma
minus
4,
1, 4.
which is C.
C, comma C, comma C.
Okay,
Oh,
if you
no.
want to write step by
Yes.
step, then yeah, I'll write one more step. C comma C comma C plus
Plus
6,
6,
comma
comma minus 3,
6, comma minus
and
3,
12.
comma
Minus 3,
minus
12.
comma 12.
12. So now this is C
C
plus
plus
6,
6,
C
is equal to
minus
C
3,
minus
Plus
3.
three.
C minus
plus
3,
12.
C plus 12.
So now it is given that this C plus 6, C minus 3, C plus 12 is equal to
4,
Comma J,
4
comma
JK.
K.
4 comma J comma K.
4, comma J,
So
comma
now
K.
this first component is equal to this first component, which means
So C is
equal
equal
to
to
minus
Equals to
2.
minus 2.
C
minus 2.
C is equal to
Minus
minus 2.
Minus
minus
2.
2.
By the way, this symbol means implies.
Yes, ma'am.
Okay, this symbol means implies.
Implies.
Okay, this symbol is implies symbol. Okay. And then you have C minus 3 is equal to J. Now you know that C is equal to minus 2. So it
Yes.
means
So J
minus
is
2
in minus
minus
5.
3 is
Minus
equal to
5.
J. So J is
-5.
minus 5. And then you have C plus 12 is equal to K.
10.
So what is your K?
10.
10. Okay. So you have found what are C, J and K. -2, -5 and 10. Okay. Fine. So we have already completed J and K here. So what is the value of J plus
5.
K?
5.
5.
5. All right. Okay. So now you should be very clear about what are vectors, what are vectors in Rn in general. N can be 1, 2, 3 or any finite whole number. Okay. Not 0, of course. 1, 2 starting from 1. So positive integer
1,
maybe.
2, 3.
Yeah. So and then how to add two vectors in Rn and how to do scalar multiplication. There is one thing I want to ask. So we have defined only addition and scalar multiplication. Using these two, how do you define subtraction?
We can scalar multiply by -1.
Yeah.
Then add the both.
Exactly. So suppose maybe I'll write it here itself. So what is subtraction of two vectors? So first you have x1, x2 and xn. And then what is minus y1, y2, yn? So here you do scalar multiplication by -1. Okay, so let us say this is your vector x and this is your vector y. Okay, so you are doing scalar multiplication by -1 for y. Okay, and then you add it with x. So you see that this is nothing but x plus minus y. So what is the subtraction you will get? x1 minus y1, x2 minus y2.
xn minus yn.
Okay, so that's why we did not define the subtraction separately, because it automatically follows from vector addition and scalar multiplication. All right. Okay, so moving on to matrices. Matrices, you already know that matrix means it is a rectangular array of numbers arranged in rows and columns. Plural is matrices. Okay, so the main important application of matrices is that we use matrices for solving system of linear equations. You see that any given data, you can look at them as vectors, and also you can look at them as matrices. Okay, so that to study the data and sometimes to study much more things, so you have to solve system of linear equations. Okay.
Excuse me,
so
ma'am.
yeah.
Ma'am, I could not understand the subtraction part which you discussed a bit earlier.
See, what is x minus y? X minus y is nothing but x plus minus y. You already have defined what is addition of two vectors, and you have already defined what is the scalar multiplication. Maybe I will put -1 dot y. So -1 is a scalar and y is a vector. What is scalar multiplication is already defined. What is vector addition is also defined. So -1 times y is nothing but -y1 minus y2 minus yn. And then you add it with x. So you will get x1 minus y1, x2 minus y2 and xn minus yn. Got it?
Yes, ma'am. Thank you.
Okay. So how these matrices are related to system of linear equation, that we can see in detail maybe at the
What is the array?
What is an array? Okay, so array, you can say it is not just a group of numbers, but it is arranged in a specific way. So group of numbers mean it is just any numbers, but here array means it is ordered in a specific way. So like boxes you can imagine. Okay, so there are some group of numbers, means array of numbers you say. So if you see numbers like this, okay, so they are array of numbers. Okay, fine. So now this has rows and columns. Okay, so what are two important notions about matrices? An m by n matrix has m rows and n columns. Okay, ijth entry of a matrix is the entry occurring in the ith row and jth column. Okay, so here m by n matrix, for example, let me take a 2 by 2 matrix. So 2 by 2 matrix means how many rows and how many columns?
2 and 2.
2 rows and 2 columns. It means it should look like something like this. So you have 2 rows and 2 columns.
And 2 columns.
So this is your row 1, row 2, column 1, column 2. Okay, so this is a 2 by 2 matrix. Now, what is ijth entry of a matrix? It means the entry occurring in the ith row and jth column. So what is the 1, 2 the entry of this matrix?
-3.
-3.
So occurring in the first row, second column, it is -3. Okay, fine.
Yes.
Ma'am,
So
not
here are, yeah.
I'm not clear on this part. 1 2th entry means
First row and second column.
So 1, 2, so 1, 2th entry means, see, it is the ith row and jth column. So entry occurring in the ith row. So I here is 1, so first row, and jth column, j is 2, so second column. So first row, second column. So this is your 1, 2th entry.
Got it. Thank you.
Okay, fine. So now here are some examples. Can you say, so this is called the size of the matrix. This is called the size of a matrix. This m by n you call the size, or sometimes order of a matrix as well. So what is the size of this matrix A? Can you tell?
2,3.
2 by 3.
So how many rows you have? 2 rows and
2 rows, 3 columns.
3 columns. So it means this is a 2 cross 3 matrix.
3.
Okay. And how many rows and how many columns are
3
here?
cross 2.
3 cross 2.
columns.
3 row and 2 columns.
Okay. And what about this?
2 cross 2.
2.
Okay. So now the same thing, if you have a name for the matrix, this ijth entry can be represented like this. So of a matrix, suppose the matrix has a name A, then this ijth entry is represented as aij.
Yes,
Okay.
ma'am.
So
Yes.
here, for example, what is your A13?
3.
3. What is your A22?
19.
Second row, second column, 100. Right? Okay. Now what is B22?
0.
Now what is B2? Maybe B32.
12.
12. This is the 12.
Now what is C11?
3.
3.
What is C21?
5.
So you understand this notation now, right?
Yes.
Okay.
Yes, ma'am.
So let us look at some special type of matrices.
Ma'am, I'm not clear on these notations. Could you please explain?
This ijth entry.
Yes, ma'am.
See, for example, A13 means you have to look at 1 means represents the row. So this is your row 1.
Okay.
So first row and 3 represents the column. In first row, what is the third entry? It is 3.
Okay.
And similarly, A22 means this is row 2. In second row, what is the second entry?
Okay.
Got it?
Got it.
Okay, fine.
Thank you.
Okay. Some special types of matrices. So now you have a square matrix. What is a square matrix? A square matrix is a matrix in which the number of rows is same as the number of columns. So you should have typically an n by n matrix. Usually we say square matrix means n by n we say. So you have like maybe 2 by 2, 3 by 3 or 4 by 4, any n by n matrix is a square matrix. Okay.
Yes.
The main thing about square matrices is that what are diagonal entries of a square matrix is something you should all know. Okay. So the ith diagonal entry of a square matrix is the ith entry. So what is ith entry? So suppose let us say you call this matrix as A. What is A11?
This is a
0.3.
0.3.
What is A22?
0.
0.
What is A33?
Minus
1.
-1.
Okay.
This is a
So you
diagonal.
see that these entries here in the diagonal of this matrix. So this is what you call as the diagonal of a square matrix. Okay. So this is the diagonal of the matrix, and each of these entries are the diagonal entries of the matrix. Okay.
Yes,
Fine.
ma'am.
Yes, ma'am.
So suppose I'm having maybe let us say 5, 9, 3, 0. So what are the diagonal entries of this matrix?
5 and
5
0.
and 0. So these are the diagonal entries. Okay. So sometimes you have this terminology also. What is an off diagonal entry?
9, 3.
They're not the diagonal entry.
Yes, exactly. Entries other than diagonal entries. Just to know.
Ma'am, entries other than diagonal entries, or the other diagonal, I mean the diagonal other than the principal diagonal.
Yeah, so 9 and 3 are the off diagonal entries here.
Like in a 3 cross 3 matrix, there
So they are
like
5, minus 7, 1, 2.80, minus 2.5.
all of them.
Yeah, yeah.
Okay.
Except the diagonal entries, whatever is remaining, all of them are off diagonal entries.
Okay, ma'am.
Okay, fine. Now you have another special matrix which is called diagonal matrix. The name itself tells you it has only diagonal entries. So a square matrix is a diagonal matrix if the entries outside the diagonal are all 0. It means all your off diagonal entries are 0. So you can have either 0 or non-zero elements in the diagonal. For example, 1, 2, 3. So first of all, a diagonal matrix is a square matrix, you should remember. Okay. And only the diagonal entry, apart from the diagonal entries, everything else should be 0. Okay. So now maybe look at this matrix. Can you tell me whether it is a diagonal matrix?
Yes, it is.
No, no.
Yes.
Yes, ma'am.
Yes, it is.
No, all the entries other than the diagonal entries are 0. It is possible that the diagonal entry is
Can be
0. Okay. For example, 1, 0, 0, 0. This is also a diagonal matrix. Okay.
Yes, ma'am. Okay.
Yes, ma'am.
So otherwise, or we can write it like
And
this.
what
Also.
if all are zeros?
Yeah, all 0 is also possible.
Ma'am, I'm
so-
having a doubt, ma'am.
Yeah.
Ma'am, in the square matrix example, there was a 3 cross 3 matrix, right, ma'am?
Yeah.
Ma'am, we can also have minus 7, 0 and 0 as a diagonal. Can we do that, ma'am? Like
See,
3,
usually
3?
by diagonal, usually this is called the main diagonal. Okay, so
Okay,
this
ma'am.
is the principal diagonal. And for this course, we are talking only about the principal diagonal. We are not considering the other diagonal in this course. So
Okay,
forget
ma'am.
about it.
Okay, ma'am. Thank you, ma'am.
Okay. Okay. So all these, including the 0 matrix, are all diagonal matrices. Okay. Fine. Now, in terms of notation, suppose I'm calling the diagonal matrix as A. What can you say about Aij when I is not equal to J?
0.
It should be
Yes.
0.
Okay. So how can you say a diagonal matrix? It is A is a diagonal matrix if it is an n by n matrix such that Aij equal to 0 for all I not equal to J. So the other way to define a diagonal matrix, since you know notations now. Okay, fine. Okay, now what is a scalar matrix? So scalar matrix is specifically a diagonal matrix. It means all the entries outside diagonal should be 0. Okay, and in the diagonal all the entries are equal. They are all same number. For example, you can see minus 5, minus 5,
Minus
0,
5,
0.
minus
This is a scalar matrix.
scalar.
And let us say 3, 3, 3.
3
This is a
scalar matrix.
scalar matrix. Okay. Then 1000, 1000, 1000, 1000. Okay. So let us say this is a 4 by 4 matrix. I will not write all the entries. Sometimes just for simpler understanding. So only except diagonal entry, all other entries are 0. So now this is a scalar matrix. Okay. What about
Okay.
the zero matrix again?
Scalar
That is also a
It's a
scalar
scalar
matrix.
matrix.
Scalar
Okay,
matrix.
fine. So now you know what is a scalar matrix. Okay, now what is an identity matrix?
This is the
All
one
the
zero
diagonal
one
entries are 1.
Yes. So you have the 2 by 2
10.
matrix 1 by 1, 1 1,
Yeah.
3 by 3
1
means
0
yeah.
0.
Scalar matrix should be a diagonal matrix, no?
Yes.
Diagonal matrix means at least one of the diagonal elements must be non-zero, no?
No. See? It can
Here,
be
in
0.
last example you gave
It
it.
can be
null
0. That
matrix.
is what we said. It can be 0. It should not. It is not given. It should be 0. It can be 0. May or may not be. Okay?
Oh, defining like that. Okay.
Okay. So this is your I2. So usually this kind of notation we are using to represent the identity matrix of 2 by 2, 3 by 3. And I4 means you know that you have 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. Okay. So these are all identity matrix. Now what is a null matrix? A matrix with all entries 0. See, there is one condition which is not there, which was there in all other cases. So identity matrix means it is a scalar matrix. Scalar matrix is a diagonal matrix. Diagonal matrix is a square matrix. So it means all this diagonal, scalar, identity are square matrices. But is there anything mentioned about null matrix?
No.
So this need not be square. Okay, it can be of any size. So for example, you can have a 3 by 2 null matrix. You can have a, can you say the size of this matrix?
1 cross 3.
1 cross 3. 1 by 3.
Okay. Square is also included, but it need not be square. Okay.
So even a single element would be a null matrix, a single 0.
Sorry.
A single 0, just one element, 1
Okay,
cross 1.
so it is a 1 cross 1 matrix. Yeah.
Ma'am, what is the use of null matrices?
What is the use of null matrix? What is the use of 0 in real numbers? The same reason is here. Okay. Fine.
No, in real numbers use 0 nothing, but here how?
See there you see that 0 is the additive identity, right? The same
Yes.
works here. In matrix also 0 is your additive identity.
Okay.
Okay, fine.
Ma'am, what's an
Is
additive
matrix
identity?
vector?
What is?
Is matrix vector?
See, if you are okay, when you move to week 3, you see that we will study what are vector spaces. So if you consider vectors as a group of matrices with certain operations on matrices defined, so it should satisfy specific condition. Their matrices are vectors. Okay, and in general sense, we usually say that the columns and rows of a matrix are vectors, but there are vector spaces which are matrices. So their matrices are vectors. Okay, so in week 3 you will see examples like that. Don't worry now. Okay.
How can we visualize matrix as we did for vector?
See, matrices visualization you can do if it is like 1 by 3 or 3 by 1 or 1 by 1, because that will again reduce to R2 or R3. But otherwise you cannot visualize anything beyond R2 or R3. Okay.
Okay.
Fine. So of course you visualize the matrices as data. So if you are having your data set and that gives your, that is one way of visualizing. If I don't know what is the visualization you mean. Yeah, that is one way you can see matrix.
No, in geometry, I said.
Okay, geometrically means you can only visualize up to R3. So either 1 by 3, 3 by 1, or 2 by 1, 1 by 2, or 1 by 1. That's all you can visualize. Okay.
Okay.
So what are triangular matrices? The word itself tells that it should have some triangular structure. Okay. So first of all, They are square matrices. Just give me a moment. I'll be back. Just hold on. Yeah. So triangular matrices, for example, they are first of all square matrices with all entries below or above. Okay, diagonal is called an upper triangular and lower triangular. So first let us look at what is upper triangular. So upper triangular means it is mentioned that all the entries below. Okay, so below diagonal is 0. So it means, so now 1, 2. Okay, so 1, 2. So which one is below diagonal? This or this? This part, right?
Yes.
So this part should be 0. So this one can be 0 or need not be 0. That does not matter. But this should be 0. This is upper triangular. And also you can see. So the remaining entries should be 0 if it is an upper triangular, right? So this is upper triangular. Do you understand what is upper triangular?
Yes, ma'am.
Yeah? Fine. So now you can also see that the same concept goes for lower triangular. Lower triangular means you should have all the entry above diagonal as
The
0.
elements are 0, then also is it upper triangle?
Yeah. So here maybe 3, 4, 0, 5. Minus 1, 0, 3, 5, 0, 7. This is 0, 0, 0. Okay, so these are lower triangular matrices. Now,
Ma'am,
yeah.
Diagonal matrices are both upper triangular and lower triangular.
Exactly, exactly. Diagonal matrices are both upper and lower triangular. Good. Good observation. Okay. So now here you see that we can also write it in terms of notation. Okay. So now what is this entry? A. If you call this matrix as A, what is this entry?
2, 1.
A, 2,
2,
1.
1.
And what is this?
2, 1.
A1. A2, 1. A2, 2.
A, 2, 1. This is A, 3, 1.
1.
This is A, 3, 2.
3, 2.
And here, what is this?
This is a
1,
A1, 2.
1, 2.
1, 2, 1, 3,
1, 3.
2, 3.
And this is
2,
a
3.
2.
So now
2.
considering these entries, here for below diagonal entries, if I am writing A, I, J, what is the relation between I and J?
If I is greater than j.
So you see that I is greater than J. So you can say that a matrix is upper triangular if Aij is 0 for all I greater than J. Same way for lower triangular, how will you say? Aij should be 0 when?
Less than J.
Less than
J
J.
is greater.
Less than
Okay.
J.
So this is how you can look at matrices with symbols as well. Okay. So in exam, whether it is given as words like this or it is given in symbols, everything you should be familiar with. Nothing should not be new. Okay. Everything you should be familiar. So that's why I'm writing everything simultaneously. Okay, fine. What about row matrix?
Vector.
Yeah.
Which
So it
contains
is simply
0 and
any
many columns.
matrix of size 1 by n, right? So maybe like 1, 2, 1, 5, 9, 1000, 2000, 3000. All these are row vectors. And what about column vectors?
Contains
Which
only column.
contain one column.
Yeah. Okay, so these are column vectors. Okay. Okay. Now next, looking at operations in matrices. How do you add matrices?
Ma'am?
Yeah.
1 matrix is also a column matrix and row matrix both?
Exactly. Yeah. 1 matrix is both a column as well as row matrix. Okay. So coming to addition of matrices. Addition of matrices is just like addition of vectors. You do it component wise. So the ijth entry and ijth entry of A and ijth entry of B added together will give you the ijth entry of the new matrix A plus B. Okay. So for example, suppose you are having matrix A is given by 2, -1, 3, 5. And matrix B is given by 7, 9, 0, -1. What is A plus B?
9,
9.
8, 3, 4.
Okay. So you see that it is just component wise addition. What is the main thing is needed for addition of two matrices? The both the
Order must be
matrices should
same.
be of
Equal component.
same order,
Same
or
order.
same size. Okay. So matrix addition is possible only for matrices of same size.
Same order.
Yeah. All right. Okay. Now, yeah.
Yes, we can assume 0, and can't we do that?
We can assume 0.
Suppose there's a matrix A which is more length than matrix B, and can we assume that there is 0 in the place and add the element which is greater?
If
I guess not.
Ma'am, he was saying that if there is a matrix of different size, but if we add 0 to make equal size, then it is possible or not?
we don't do that usually. We usually just say that addition of these two matrices is not possible. Okay. So adding zeros, that we don't do in this course. No.
Not adding, just assuming zeros for purpose of addition.
Okay. So if you are assuming that you are forming a new matrix and then make zeros, yeah, fine. Okay. But we are never going to do that in this course. Okay.
But ma'am,
generally it's right, no?
extra element
Sorry?
if there is no any zeros, ma'am.
Is it right? Out of the course, is it right?
Zero will be help in like adding the matrices if they are in different sizes.
But we are not going to do that. So yeah, you can do that, put zeros and add, but that we are not doing here. So if you are saying some datas are missing and then you put zeros, yeah, that is something different. But here we are not doing anything like that. Okay.
Yeah, ma'am. Actually, yeah, I'm also aligned with you, ma'am.
Okay. Fine. Okay, so scalar multiplication. What is scalar multiplication? It is just like scalar multiplication of vectors. Multiplying a matrix means you see that the product of a matrix A with a number C means each entry of the matrix you are multiplying by the scalar. Okay, so for example, if you have maybe some simple matrix -1, 3, 0, 2. What is 2 times of this matrix?
-2,
minus 2, 6, 0, and 4.
0 and 4.
Okay, fine. So now there is one question I'm going to ask here. So can you write every scalar matrix as a
Identity multiplication.
scalar multiple of identity?
Yes.
Yes, ma'am.
Yes.
Yes, ma'am.
Yes, right?
Yes,
So for
ma'am.
example, if you have a scalar matrix like this, which is of size 2 by 2, then you write it as minus 2
Minus
times
times identity.
0, 1.
so minus 2i, right? So the scalar multiplication is not just for square matrices, for any size, right? So -1 times of 1, 0, 3, you will have minus 1, 0, minus 3. Okay. So this is about addition and scalar multiplication of matrices. Okay. So the complicated part is multiplication of matrices. Okay. So how do you multiply two matrices? So we will start with a very simple matrix. So which is so what is this type of matrix called?
Row matrix.
What
Row
is the size
matrix.
of this matrix?
1 cross 3.
1 cross 3.
Okay. What is the size of this matrix?
3 cross 1.
This matrix is called a
3 rows.
Column matrix.
column matrix. Okay.
Column matrix.
So, for example, here we have considered a simple row matrix and a column matrix. Okay. So how we are going to multiply this row matrix and column matrix? So this row we are going to multiply with this column. How? First entry with the first entry, second entry with the second entry, third entry with third entry. A, D, B, E, C, F, and then we have to add everything. Okay. So you are having 1 cross 3. So this is 3 here and 3 cross 1. Okay. So you see that number of columns of first matrix is equal to what?
Number of
Number
rows.
of rows of the other column.
Rows of the second.
Yes, of second matrix. So only if this is there, you can do matrix multiplication. So this is the first condition for matrix multiplication. The number of columns in the first matrix should be same as the number of rows of the second matrix. This is the first condition. Okay. And what is the size of the resulting matrix? So this is your RC. What is the size of the resulting matrix? Now this is just a scalar. AD plus B plus.
Of first matrix into
So this is
number
just
of
one row.
columns of second matrix.
Yeah. So this is number of rows of first cross number of columns of second. So this is the size of the resulting matrix. So this is true for any matrix multiplication. So now you are having another matrix here, A, B. So now what is the size of this matrix A?
3 cross 3.
3 cross 3. And what about B?
3
cross 3. So is matrix multiplication possible for AB?
Yes.
Yes, ma'am.
Okay, so what is the size of the resulting matrix?
3 cross
3
Yes,
3
so
cross
it is again a 3 cross 3 matrix. Now, how are we going to do the matrix multiplication? You just have to remember the first step. So remember, now suppose this is your R1, R2, R3. For the first matrix, you are going to consider the rows, and for the second matrix, you are going to consider the columns. Okay. So first row and first column.
First column.
First row and first column, how do you multiply? A11, B11 plus A12, B21 plus A13, B31. Right? So this is row 1 times C1. Do you agree with me?
Yes, ma'am.
Okay. Now for the second entry, R1, C2. First row, second column, A11, B12 plus A12, B22 plus A13, B32. Similarly, this is R1, C3. And what is this? Can you tell? This is
R2 to C1.
R2C1.
This is R2,
R2 C2.
R2,
R2 to C3.
C3. This is
R3 C1. R3 C2. R3 3
okay. So do you understand how to do the matrix multiplication? If you know this first multiplication, then you know matrix multiplication for any size matrix. Okay. So there is a notation for this multiplication. Just notice what is happening here. A11, B11, A21, B21, A13, B31. So something is going on. So can you tell me what is the IJ for this one?
Ma'am, the ith entry, sorry, the ith, what should I say?
IJJ.
Ith entry in this resultant matrix So the I come from the row number from first matrix, and column come from the j
Exactly.
comes from column number of second matrix.
Exactly. Okay. So now, for example, let us look at what is AB11. Okay. So AB11 is, from this expression, you can see that summation I is equal to 1 to D. Yeah. Let me first write and then I'll explain and then you'll ask, you can ask your doubts. Okay. Here I is, what is your I in this case?
1.
So this is K. There is a mistake here. This is K is equal to 1 to N. So your A1, K, B, K, and J is again 1. So if you expand this summation, what will you get first? When you put K is equal to 1, what will you get? A11.
A11, B11.
And when you put K is equal to 2?
A12, B21.
And K is equal to 3?
A13,
A13.
So do you see that this is the first expression?
Yes.
Okay. So this is the general expression for the ijth entry of matrix multiplication. Okay. So this is an important expression you should remember. Okay. So ijth entry, you have this kind of an expression. Okay. So as I told in the beginning, multiplication of matrices A and B is defined only when the number of columns of A is same as the number of rows of B. Okay. So maybe I will do some quick examples. So 1, 2, 2 minus 1. So how many rows and how many columns are here? What is the size of this matrix?
2
cross 2.
Okay. So now let me write. So what is the size of this matrix?
2 cross 1.
2 cross 1.
So is this matrix multiplication possible for AB?
Yes.
Yes, ma'am.
Yes, ma'am.
What is the size of AB?
2 cross 2.
2 cross 1.
2 cross 1.
Yeah. Tell me now, what are the entries of the matrix AB? What is the first entry?
1. First
AB
is a 1.
1.
So it
1
is 1
plus 1 plus 0.
0.
Plus 0.
and then the
2.
second is
2 plus 0.
Plus
2 plus
0.
0.
so it is 1 2.
1.
1
So
2.
is A possible in this case? Is BA possible?
Not
No,
possible.
ma'am. No.
Not defined. Right? BA is not defined because of the order of the matrix. Okay. Now maybe let us take A is equal to 1 minus 1 3. Now what is the size of this matrix?
1 cross
1
3.
cross
1 into
3.
3.
Now let us say B is
3 cross 2.
yeah
3
3
cross
cross.
2.
Now is AB possible?
Yes, ma'am.
Yes.
Yes, ma'am.
Yes, ma'am.
Size?
1 cross 2.
1 cross
1
2.
cross 2.
1 cross
Yeah.
2.
What are the entries?
3 plus
3 plus
plus
0
0
plus 3.
plus
3 plus
3.
0 plus 3.
And then
Minus 1, minus
Minus
5,
Minus
1 minus 5 5
0 plus 0
plus 0.
so
6,
6.
minus 6.
minus 6.
okay. So now another example. A is equal to 1 0 minus 1 1. B is equal to, I'll simply put a diagonal matrix. So now they are of the same order, so there is nothing to check. So what is the size of the resulting matrix? Again, it is a
2 cross 2.
2 plus 2.
yeah.
2
So
plus
this
2.
is 2 cross 2. This is 2 cross 2, and this is also 2 cross 2. Okay. So now what is A into B?
2 plus 0.
2 plus
1
2.
and
Or 0 plus 2.
0 plus -2.
0 minus 2.
Yeah.
0
0
plus 0.
0 plus
0.
0.
0 plus 0.
Okay. 0 plus 0.
No.
0
0
plus
plus 2.
2.
2 plus 2.
So the resulting is
2 minus 2 0 2.
okay. So is it
Yes.
possible to express AB as a scalar multiple of A?
Yes.
Yes, ma'am.
Yes,
Yes,
ma'am, it
sir.
is. We can use 2.
Yes.
2 times A.
Yes.
So can you observe something?
Yes, ma'am.
If we
Ma'am, B
multiply
is
a matrix by identical matrix, the result will be same.
So if you multiplying a matrix with
If
a
you
scalar matrix is nothing but multiplying with the scalar itself. Okay. So this is a scalar matrix, and when we multiply a matrix with a scalar matrix, you just have to multiply with the scalar. That's all. Okay. Is that clear?
yes, ma'am.
Yes, ma'am.
Ma'am, are size and order the same?
Sorry.
Are
Yeah.
size and order of a
Interchangeably
matrix?
used. Yeah. Okay. So another simple example, let me take. A is equal to 1, 5, 3, 2. B is equal to 1, 0, 0, 1. Without calculating, can you quickly tell what is AB?
1
Ma'am,
1,
1 5 3 1.
1532.
What is BA?
BA is also
Same,
A.
ma'am.
again,
Same.
1
The same.
1532.
1532.
Okay. Now, so this is the general remark. If you take the identity matrix and multiply with the any matrix, the resulting matrix is again the same matrix. Nothing is going to change. Okay. Fine.
Yeah.
So this is about matrix multiplication. Here are some properties of matrix addition and multiplication. So it is associative when with respect to addition, also associative with respect to multiplication. So the order of addition or multiplication does not matter. And it is commutative with respect to addition. What about with respect to multiplication in general? So let us say you are having.
No, because we saw above only now.
No, here this multiplication was not possible, but suppose let us say multiplication is possible. Okay, let us say maybe, yeah.
dimension changes. Dimension may change.
Suppose let us say both are of the same size. Now what about AB? What is your matrix AB? 2 minus
2
1
plus
and then 0 plus 1. 0 plus 3, 0 minus 3. Is this correct?
Yes.
yes, ma'am.
Yes, ma'am.
1, 1, 3 minus 3.
3 minus 3.
What about BA?
2 plus
2
0.
minus 1.
2 0.
Plus
2
0 and then minus 2
2
plus
plus 0.
0 and then 1 minus 1. So 1 plus 0 and then minus 1 minus 2,
Minus 3.
which is 2 minus 2, 1 minus 2.
1 minus
and
4.
minus 4.
So is AB and BA same?
No, ma'am.
No, ma'am, they are not.
So AB matrix multiplication, is it commutative?
No, ma'am.
No, ma'am.
Okay. So when matrix multiplication in both sides is possible, even then it is not necessary that they are commutative. Okay. And of course, you have the linearity property when you do scalar multiplication, you can split them. Here you see that for multiplication also it is valid. And you have the final distributive property for matrix addition and multiplication. Okay. Fine. So these are some basic properties on this operation. So the next important operation is what is the transpose of a matrix? What is the transpose of a matrix?
Interchanging rows by columns.
Changing rows by columns.
So you interchange the rows and columns of a matrix. So what does that mean? Suppose if A is an m by n matrix, what is the size of A transpose?
N cross N.
N cross M.
So let us say if you are having A is 1 minus 3 0. What is A transpose?
1 minus 3 0 is the column.
3 0. Different order.
Okay, so the size of A is here
1 cross 3.
1 cross 3.
and A
3.
transpose is
3
3
cross
cross
1.
1.
okay. And suppose let us say A is a square matrix, we will call B. B is a square matrix. What is B transpose?
This is a 2,
2
3 is a
minus 1,
3 is
3,
a column
4.
minus 1, 4.
2 minus 1, 3, and
First
4.
column minus
Yes.
Okay, fine.
Same order.
So how do you
Why we need
represent?
to do transpose? Why we need to do transpose?
Why we need to do transpose? See, just like how certain operations or matrices are useful, transpose of matrices are also useful. So in some cases, what happens is that if you do transpose, certain properties are easily visualized. So when we do those properties, maybe I can tell you. So it can easily visualize certain properties. So that is why transpose is useful. And rows and columns have similar properties. So transposing is not going to change most of the important properties. So if you have a better visualization without changing properties, is it good or bad?
It is good, ma'am.
Good. That is why we are doing this transposition. Okay. So you have a better visualization of certain things without affecting things. Okay. Fine. When you do this determinant, particularly this transpose is handy in certain examples. We can see it. Okay. Fine. And yeah, so transpose you have seen. Now, in terms of notation, how can you tell? So, A transpose, what is the ijth entry of A transpose? How can you tell? Can anyone say what did we do?
Change rows.
JI.
AJ.
A of Ji.
Yeah, they are of I.
Okay. So, this is the ijth entry of A transpose. Okay. So, what is the transpose of a upper triangular matrix?
Lower
So, let
triangular matrix.
Lower triangular.
1 0 minus 3 2.
Lower
What
triangular
is the
matrix.
Longer
transpose?
triangular matrix.
1 0.
1 0 minus 3 2.
Yeah. Okay. So it has become a lower triangular. Similarly, lower triangular will become a
Upper triangular
upper
matrix.
triangular when you do the transpose. Okay. So does
Ma'am, is this valid for all order?
sorry?
3 by 3.
Why will
You can try
transpose
it out
will
and tell me.
for all
It is a
order?
very simple question. So you can try it out and you can see it yourself. What is the answer? What should be the answer? Is it true for any order?
I will try.
Okay. Fine. See, your Aij and Aja are interchanging and you know the respective definition I greater than J, J greater than I conditions. So use that and it is easy to see for any order if you want. Okay. So the next type of special matrices are symmetric matrices. What are symmetric matrices? So if you have A transpose and A to be same, then such matrices are called symmetric. So they are symmetric about the diagonal. Okay, so the diagonal kind of acts like a mirror. For example, 1 minus 3 minus 3, 2. So if this is your A, what is your A transpose?
1
this
minus
is a
3
1 minus 3
1 minus
minus
3 3
3
minus 3 2.
2.
So you see that A transpose is same as A, right? Now suppose you have A is equal to, remember symmetric matrices is possible only when you have a square matrix because A transpose the size should be same as A. So that is possible only for square matrices. Okay. Now let us say minus 1 minus 3 0, 2 1 3. Can you tell what is this A21 entry?
minus 3
Minus 3
What is
0
A31?
0 0 1.
1.
1.
Okay. So this is these are the entries so that A transpose is equal to A. So in terms of notation, how can you tell? So Aij
equals to AJ.
Equals to
should
AJ.
Equals to AJ.
for all ij. Okay, fine. Now, what is a skew-symmetric matrices?
Ma'am,
Yeah.
you said that this transpose is defined only for the square matrices.
No, no, no. I said symmetric matrices are defined only for square matrices.
Okay, okay.
And a diagonal matrix is also symmetric matrix.
Which matrices?
A diagonal matrix.
Yes, diagonal matrices are always symmetric. Okay, diagonal matrix, scalar matrix, identity matrix, all are symmetric.
Ma'am, could you please pardon this symmetric matrices? How
See.
we derive this A part?
See, A transpose is equal to A. So it means what I already told you. The ijth entry of A transpose is nothing but A ji. That is the definition of transpose, right?
Right,
A
right.
transpose ij is A ji. But we
Correct.
see that this is same ijth entry. But we see that it is same as your Aij, which is Aij. Okay? A transpose is equal to A. So Aj is equal to Aij. Okay?
Okay.
Is it for transpose a square matrix is allowed or any matrix we can use?
Transpose, we have seen examples for non-square matrices also. For transpose in general, you don't need square matrices. Only for symmetric, you need square matrices.
Okay, ma'am.
Okay. And you see that here, this is the diagonal. And you can see that the diagonal kind of looks like, acts like a mirror. So either side, you see the images are the same. If you imagine this as a mirror, both are looking same. Okay? Fine. That is why it is symmetric about the diagonal. Okay. So what are next? So what is next? So you have skew-symmetric matrices. So what are skew-symmetric matrices? An n by n square matrix is called a skew-symmetric matrix if A transpose is equal to minus A. So in that case, so first let us look step by step. So A transpose ijth entry is, what is this?
Minus EJ, EJI.
It is
A
as minus
J I J.
Aij, but actually what is this? A Ji, right?
J. Yes, ma'am.
Yes, ma'am.
Aji is same as minus Aij, right? Now what happens when I is equal to j?
Value becomes 0.
Zero.
So Ai is equal to minus Aii. What does this imply?
2 times AI is equal to 0.
Yeah. So it means, what does this mean? All diagonals are,
Diagonal element should be zero.
yeah, all diagonal entries are 0.
Ma'am, could you please explain this part again?
See, what happens to A transpose, ijth entry of A transpose, it is same as minus Aij, correct?
Yes, ma'am.
Now, by the definition of transpose, A transpose ijth entry is Aji. Okay?
Yes,
So,
ma'am.
Aji is equal to minus Aij. What happens if I is equal to j? So, I is equal to j means you put I for both this. So, then if I is equal to Aii is equal to minus Aii. So, when is a number equal to the negative of its number? Only when it is 0.
0.
Okay?
Okay, got it, ma'am.
Yeah. So 1 minus 1 0 0. Is this a symmetric matrix?
No.
So
No, ma'am.
we have to just reverse the diagonal matrix in this case. So 0 minus 1 1 0. Now is this a symmetric matrix?
No, ma'am.
Yes.
No, ma'am.
No,
The first
the
one was
first one was
symmetric.
symmetric.
The first, okay, I'm asking skew symmetric. I'm sorry.
Symmetric.
Oh,
Yeah.
yes, ma'am. It is.
Yes.
So suppose this is A. What is A transpose?
Oh, minus.
0 1
Zero
minus
in
1
column 0
0.
minus 1.
0, 1, minus 1, 0.
Yes,
So
ma'am.
now this is nothing but minus
Minus
A,
8.
right? Okay.
Yes, ma'am.
Now,
Yes, ma'am.
similarly, let's construct an example for 3 by 3 case. First of all, our diagonal entries should be 0. Can you tell what is this entry?
3.
3 minus 2
3
minus 1.
Minus 1.
3 to 1.
Minus 1.
So then you see that suppose this is B, then B transpose is equal to minus B. All right? Okay?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, fine. So up to this is
Yes.
everything clear? Yeah?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Fine. Okay, so here are some exercises. Which of the following statement are true? Option 1, any diagonal is a scalar matrix.
No.
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 Scalar matrices may not be square matrices.
False.
No.
Scalar matrices
False.
must be square matrices.
Yes.
True.
True. True.
Any
This is the
scalar
true.
matrix is an identity matrix.
False.
False. False.
False.
Okay. Suppose P, Q, R, and D are given like this. First of all, let us write the size of these matrices. What is the size of P?
3 cross 3.
3
Ma'am,
cross
it
3.
is saying
3
any,
cross
not
3.
every. तो ये
1.
4 वाला option सही नहीं होगा.
Sorry, what is your question?
In option 4, it is saying any.
Yeah.
Any scalar matrix, not every.
See, any means you can take any scalar matrix. So I am taking 2, 2. So this is a scalar matrix. This is any matrix. So is this identity?
No.
Yeah.
Identity is a 1 0 1 0 1.
Yes, that is why this is wrong. Okay, fine. So what is the size of Q?
1 cross 3.
1 cross 3.
1 is 1
4
into
cross
3.
1
1
cross
cross
3.
3.
3 cross 1.
3 cross 1.
So what is the order of
D.
PD?
This is a 3 cross 1.
3 cross 1.
Cross 1.
Cross 1.
So second option is incorrect. The matrix QD.
What is correct, man?
QT.
1 cross 1.
1 into 1.
Okay, what about DQ?
3 cross 3.
3 cross 3. Right? What is
3
QD?
cross 3.
So already QD we have seen it is a 1 cross 1 matrix. QR.
Not defined.
Not
Not
defined.
Not defined. Not defined.
P plus Q.
Not defined.
Not defined.
Yeah.
Not
P-
defined. Not defined.
Yeah. Okay. Suppose A is this matrix and B is this matrix. Which of the following options are true? Everyone take paper and pen. Quickly find what is A squared and B squared. Everyone do it quickly. Calculate what is A squared, A into A, and calculate what is B squared, B into B. Everyone do it quickly and tell me the answer.
A square equal to I.
A square equals to I, B square equals to 0.
0.
So this is nothing but I,
First one is correct, ma'am.
and B square is 0.
0.
Null matrix.
Option 1.
So option 1 and option 4. Okay. So there is a special name for such matrices. Do you know the name? Anyone?
Null matrix.
Null matrix.
Null matrix.
So your B square is null matrix, but if there is a name for such B for which the power is 0.
Nilpotent.
Exactly. Nilpotent matrices. Okay. So such matrices are called nilpotent. So the matrix itself is not null, but some power of it is 0. Such matrices are called nilpotent matrices. Just for your information. We are not going to use it. Okay.
Ma'am, can you say it again? What is the name of the matrix? Null?
Nilpotent.
Nilpotent.
Okay. Okay.
It is
Suppose
a nilpotent.
B is non-zero, but B square is 0.
Okay, ma'am. I got it. Thank you, ma'am.
Okay. Suppose A is a 3 by 3 scalar matrix and the first 1/1 entry of the matrix is 4. Suppose B is a 3 by 3 matrix such that ijth entry is equal to I squared plus j squared. Find the 2 entry of 2A plus B. So what is your B matrix? Can you quickly tell me?
12, ma'am.
B matrix is 2.
Answer is 12. Answer is 12.
Sorry?
He's telling
5.
answer.
It's
0. So this is 1 1 position. This is 1 2
5.
position.
5.
So 5
1 plus 2 square.
10.
10. And here?
Same thing.
5.
10.
And here?
2 square 4.
Yeah.
4 plus 9, 14.
This one is incorrect. Tell me the correct answer.
8.
8, ma'am. 8
And then?
and 6.
Yes, 8.
9, ma'am. Oh, down. Diagonal line.
9 plus 4, 13.
Yeah.
13.
9 plus 9, 18.
9, ma'am. 18.
Okay. So this is the matrix. Now, what is the type of this matrix? Can anyone quickly tell? Just to observe.
Symmetry.
Symmetric matrix. Right?
Symmetric.
Symmetric matrix. Now, 2A plus B, 2 entry. So the 2 times of A22
8
plus B22. What is your B22?
8.
8. B22 is 8. What is A22? So what is your matrix? A is a scalar matrix and the first entry is given as 4. So what is the second A22 and A33?
4.
4.
And the remaining entries are?
0.
4 plus 8, 12.
So 2 times of 4 plus 8. You have to be patient. Okay. 16. So the final answer is 16. Is this correct? Yeah?
Yes,
Ma'am,
Yes,
ma'am, could you please explain that B matrix again? I was not able to understand that.
See, here what we have just did is that, say the position of the matrix, you should remember that's all. This is 1 1 position, 1 2 position, 1 3 position. This is 2 1, 2 2, 2 3. This is 3 1, 3 2, 3 3. Now what you are doing? 1 squared plus 1 squared, 1 squared plus 2 squared, 1 squared plus 3 squared. Same.
Okay.
2 squared plus 1 squared and so on. Now clear?
Yeah, clear. Thank you, ma'am.
Okay. Okay. Suppose A is this matrix and A squared minus alpha A plus I is equal to 0 for some alpha in R. Find the value of alpha or small a or alpha. What is this notation? I don't know. And let us say alpha. So now find A squared. Everyone find A squared quickly and tell me what are the values of A squared.
1, 4, 16, and 49.
1 4
16, 49.
49.
I did not calculate. Is this same for everyone? Yeah?
Yes, ma'am.
Okay. Are you sure? I thought someone will answer. What is A square?
I'm wrong, ma'am.
Ma'am, wrong.
Why
It's
you
incorrect.
are
A
so
square
quiet?
is
I was waiting for a quick answer. Why you people are so
minus
slow?
7, minus 12, minus
This
24.
is how you do A square. You have just squared each entry. A
Minus
square
7,
is nothing but A into A, right? Do
Yes,
again.
ma'am.
minus 7, minus 12, minus 24 to 41.
Yeah, that is correct.
So 1 minus 8 minus 2 plus 14 and then 4 minus 28 and then minus 8 plus 49. So what is the answer? Minus 7, 12, minus 24.
Minus 7, minus 2.
Is this correct?
Yeah, this is correct.
Yes, ma'am.
Okay. Now what is given to us? A square minus alpha A plus I is 0. So let us do this operation. Minus 7, 12, minus 24, 41 and then minus alpha 2 alpha, minus 4 alpha, 7 alpha, and then identity 1 0 0 1.
Subtraction sign before alpha.
And we can move this identity matrix to
In
other side.
Yes.
That
The
is fine.
equation is minus.
You can do it anyway. So what is that you are getting? Minus 7 plus alpha plus 1 is 0. So what is alpha then?
6.
So you can just verify it using the next equation. 12 minus 2 alpha is equal to 0. So alpha is
The equation is incorrect. It's minus alpha A.
Yes.
Ma'am, multiply by minus sign inside the equation. See this.
Correct only. Correct.
Yeah.
That is the same thing.
It is correct, ma'am.
Yeah.
Okay, fine. So your alpha is 6. So do you notice something here? What is the sum of the diagonal entries?
6.
6. Right? So the
That
sum
is
of
when it is
diagonal
added for
entries is 6.
alpha.
Yeah, so maybe later on when we, maybe characteristic polynomial is not here. Okay, just you see that this is 6 and this coefficient is also 6. When you look at the determinants, you will see that the determinant is going to be 1.
Yeah.
So this is a special equation, not any random equation. Okay, so what is the trace of a matrix? Trace is nothing but sum of all the diagonal entries. So for example, 1 minus 3, 2, 4. So what is trace of A?
5.
5.
5. So suppose let us say A is a skew-symmetric matrix. What is trace of A?
0.
0.
What, suppose you have an identity matrix of order 5. What is trace of
5?
5. 5.
Okay, fine. So you know what is trace of a matrix.
How A is skew-symmetric A equal to 0?
What are the diagonal entries of a skew-symmetric matrix?
0.
All of them should be 0. That is what
Yes,
we
ma'am.
saw.
Yes, ma'am. I
Yeah.
got understand.
Yeah. Okay, so up to this, is everything clear to everyone? Yeah.
Yes, ma'am.
Yes, ma'am.
I guess
Yes, ma'am.
now it's not the time to start a new topic. So maybe we'll stop with matrices in this session. In the next session, you can see about system of linear equations. All right.
Okay, ma'am. Okay, ma'am.
Okay.
Ma'am, last
When
Sunday's
we have
class,
session.
ma'am,
The
last
next
Sunday's class was not conducted. So, is there a replacement class for that?
sorry, can you please repeat your question?
Ma'am, last Sunday's class, which was scheduled for the scheduled as the first session, it was not conducted. So, is there a replacement class for that?
No. Did you look at the schedule?
It is Sunday, Thursday, Saturday, and Sunday.
Yeah. So all the weeks are already covered. Did you check that? So week 1 to 11, including the revision sessions, are already planned and it is there in the sheet. Did you check that?
Ma'am?
I can see in the which sheet, ma'am, you are referring? Sorry.
There is a Google sheet I have shared. Did you check that? I have shared it in Discord as well as in the calendar.
No, ma'am, I haven't.
When you start, ma'am?
But
I
ma'am,
have
could you
shared it.
please share it again?
Can you share now?
Okay, the Google sheet link I can share now. Just hold on.
Ma'am, okay.
The next session is on the Saturday.
The next session is on Sunday. So TA session is on Saturday and instructor session is on Sunday.
Also, ma'am, where can we access the PDF of this?
So as I told you, the drive link I will share you in the Google sheet which I am sharing here.
Okay, ma'am. Okay. Thank you so much.
So in the same Google sheet, I will share you the drive link. In the drive, I will be putting all the PDF notes. Okay.
Sure, ma'am. Thank you.
Excuse me, ma'am.
Yeah.
Ma'am, here, ma'am, in the previous question just now, we have